Hello and welcome to Engineers Mindset Academy. So in today's class, we are going to begin the very first series on Laplace transformation. Alright, so I'm going to be making 3 separate videos for the introduction because I'm targeting the table of standard values which we are going to be needing to calculate differential equations from Laplace transformation and of course partial fraction from Laplace transformation. As a result of that, we are going to be covering about 7 different table of standard values. So I will incorporate the 7 of them in 3 different videos. Okay, because this table of standard values will aid us as we go deep into Laplace transformation. Now, what is Laplace transformation? The Laplace transformation of a function, let's say f of t, is simply given as integral from t is equal to 0 to infinity of that function f of t multiplied by exponential minus st dt. So this is how to denote or solve your Laplace transformation. So L here indicates Laplace of the given function f of t, and it is simply an integral from t equals to 0 to infinity of the function multiplied by exponential st okay, times dt. So you're seeing again that this function is multiplying the exponential function, just like we did in the Fourier series videos. Okay, so which means we are going to be what? Employing our integration by parts, because this is what? Product integration. The function multiplying by an exponential function under an integral, which means we are going to be making use of our product integration. And what is product integration? Simply integration by parts. The formula is given as integral of u dv is equal to uv minus integral of v du. This is the formula to calculate integration by parts. We did all of this in our Fourier series videos. Now, I said always consider u to be the given function. Whatever function you're given, let u be that function always. And then dv, just like in the Fourier series, in this case now dv becomes what? Exponential minus st dt. Alright, now we have about 7 table of standard values which we need to know to be able to solve any problem, especially in differential equations or partial fractions involving Laplace transformation. So we need about 7 different table of standard values, and in this video we are going to be covering 3. The first is considering the Laplace transformation of a constant. Okay, so the first will be Laplace of a constant. Laplace of a constant. So if you're asked to find the Laplace transformation of a constant, how do you go about it? Now let's simply use a to denote our constant. Okay, let's say we are asked to find Laplace transformation of a, where a is a constant value. Now this is equal to, from the formula, integral from 0 to infinity. The function f of t now is a, so we're asked to find La. This simply means f of t, the function itself, is equal to a. All right, so we're looking for Laplace of a, which means a, remember from the formula, Laplace of f of t. So f of t becomes a function, and the function is simply a, which is a constant. Therefore, this is now equal to, in place of f of t from the formula, you attach a exponential minus st times dt. This is the notation. But we know that a is a constant. For every constant under an integral, you always pull it out of the integral sign. Hence, Laplace of a is equal to, let's pull out a, since a is a constant, it becomes a integral from 0 to alpha exponential minus st dt. Okay, this is infinity. Now this is equal to a. Now you know that to integrate an exponential function, I've said this over and over, to integrate an exponential function, what do? Differentiate the power with respect to what? Where you're integrating to, in this case now dt. So differentiate the power of the exponential function and then divide the exponential function by this derivative. The power in this case is minus st. That's the power. So if I differentiate this function with respect to t, I'm simply going to have what? Minus s as the result, because t here is to the power of 1. So if I differentiate t here, it becomes 1. Hence, I'm left with what? Only x. Okay, so I have minus s to be that derivative. Use this derivative now to what? Divide the exponential function itself. So you simply have exponential minus st all over minus s. So this becomes what? This integral. Hence, we have here to be a into exponential minus st all over minus s. Put in your limit from 0 to infinity. You have this. Therefore, Laplace of the constant a is now equal to, let's put out 1 over minus x. Let's factor this out. That means I'm going to have minus a all over s, or you can simply say a all over minus x is still the same thing. Hence, I'm left with exponential minus st, okay, from 0 to infinity. I have this. Now, let's put in the limits. Wherever you see t, since I'm integrating with respect to t, this is the t. That means wherever you see t, put in the limit, upper limit minus lower limit. This is now equal to minus a all over s into upper limit comes first. It becomes exponential minus infinity times s, because this is st. In place of t, t becomes infinity. All right, minus lower limit. Lower limit is now what? 0. So it becomes minus exponential 0 times s. All right, I have this. Now, Laplace of a is equal to, I have minus a all over s into, mind you, exponential to infinity is undefined. Hence, it is considered as 0. So this is now 0 minus, again, 0 times x is 0, exponential of 0, any variable to the power of 0 apart from 0, any variable to the power of 0 is 1. Okay, so exponential to the power of 0 becomes 1. So this is simply 0 minus 1. All right, and I have this to be equal to minus a all over s. 0 minus 1 remains minus 1, so times minus 1. And this is equal to, minus cancels minus, I'm left with what? A all over s. This simply means that the Laplace transformation of every constant, Laplace of a is simply what? A all over s. Now, what is a constant? A constant is simply a number. So, which means if you're asked to find the Laplace of 1, the answer is simply what? 1 all over s, because 1 is a constant. If you're asked to find the Laplace of 2, the answer is simply 2 all over s. If you're asked to find the Laplace of 5, the answer is simply what? 5 all over s. If you're asked to find the Laplace of 10, the answer is simply what? 10 all over s. So this is the first table of standard value. You have to know it. You don't need to solve all of this, especially when we're dealing with differential equations using Laplace transformation or partial fraction using Laplace transformation. You don't need to cram all of this or solve for this. Whenever you encounter Laplace of a constant, it is simply that constant divided by s. It's as simple as that. So that's the very first table of standard values. Let's move now to the second table of standard values. Now, in the second table is when you consider the Laplace transformation of an exponential function. Okay, the Laplace transformation of an exponential function. That's the second table of constant values. 2. Laplace of an exponential function. Laplace of an exponential function. So let's see the function itself. F of t is given as exponential a t, something like this, where a again is a constant. But in this case, let's use a real value now. Let's say this is exponential 2t. Of course, a there stands for what? A constant. Now we're considering it to be 2. So let's say we're asked, this is the function, and we're asked to find the Laplace of this function. So Laplace of exponential 2t. Again, this is equal to, impute that into the formula, integral from 0 to infinity, f of t times exponential minus st dt. You put that in place of f of t, you have integral from 0 to infinity. In place of f of t becomes exponential 2t multiply exponential minus st times dt. This is your Laplace. Now, this is equal to integral from 0 to infinity. Notice that I have exponential functions multiplying themselves. And from the law of indices, when two numbers or two alphabets having the same base multiply themselves, what do? Pick one of the number or one of the alphabet and add their powers. They have the same base, exponential and exponential, multiplying themselves. You simply pick one of the exponential and you add up their powers. What are the powers now? 2t minus st. So you have 2t minus st times dt. So this is actually integral from 0 to infinity. Exponential, of course, t is common between them. This becomes 2 minus s times t dt. So we just factor t because t is common between the two of them. So it becomes 2 minus s times t and times dt. You have this. Now, you have to integrate this function. To To integrate an exponential function, remember, you differentiate the power. Differentiating the power, use the result obtained from the derivative to what? Divide the exponential function itself. That gives you the integral of an exponential function. Now, what is the power in this case? Power is 2 minus s times t. I have this. Hence, if I differentiate this function with respect to t, I'm simply left with what? 2 minus s. So this becomes what I have left. Because, of course, t here is to the power of 1. And since it's product rule, remember, keep the whole of this, differentiate t. You have 1. 1 times everything here remains 2 minus s. Now, keep t, differentiate everything here individually with respect to t. Since none of them contains t, it becomes 0. So the result is simply what? 2 minus s. Okay? So which means that integral will give me the Laplace of exponential 2t is now equal to, this integral simply gives me, remember, exponential 2 minus s times t all over 2 minus s. Okay, putting your limit now from 0 to infinity. I have something like this. Okay, so I can decide to factor out 2 minus s. So this becomes Laplace of exponential 2t is equal to, this becomes 1 all over 2 minus s all into exponential 2 minus s times t from 0 to infinity. Now we'll put in our limits. This is equal to 1 all over 2 minus s into exponential, upper limit comes first. This is 2 minus s times infinity. Upper limit is infinity. Or simply, you can simply say exponential infinity multiplies 2 minus s, okay, minus lower limit. Lower limit is 0. So it becomes exponential 0 multiplies 2 minus s. You have something like this. So Laplace of exponential 2t is now equal to 1 all over 2 minus s into, of course, exponential to infinity once again is undefined, so you completely treat it as 0. Again, you have 0 times 2 minus s, automatically everything here becomes 0. So you have exponential 0, which is 1. So this becomes 0 minus 1, okay? And this is actually 1 all over 2 minus s multiplied by 0 minus 1 is minus 1. Hence, the Laplace of exponential 2t is simply equal to what? It becomes minus 1 all over 2 minus s. Now, you can rearrange this equation, letting negative sign or multiplying top and bottom by negative 1. So let's simply multiply both numerator by minus 1 and also denominator by minus 1. Of course, this is the same thing. Minus 1 divided by minus 1 is 1. So you're simply having the same result. So minus 1 times minus 1 here simply gives us what? Plus 1 all over minus times plus 2 becomes minus 2. Minus times minus s becomes plus s. So this is actually saying s minus 2. Hence, the Laplace transform of an exponential function. Alright, so we said the Laplace transform now of exponential 2t as obtained there now becomes what? 1 all over s minus 2. Not forgetting, we are supposed to do Laplace transform of a constant exponential at. We'll use this to start. So that means the Laplace transformation of every constant is simply 1 divided by s minus that constant a. It's as simple as this whenever it is an exponential function. Hence, the Laplace transform of exponential 3t, without having to solve, you should know. The Laplace transform of exponential 3t becomes what? This is equal to 1 all over s minus 3. It's as simple as this. The Laplace transformation of exponential 10t is simply equal to 1 all over s minus 10. It's as simple as this. So always, Laplace transform of any constant, let's say exponential 15t, is simply equal to what? 1 all over s minus 15. So always keep this in mind. The Laplace transformation of an exponential function always is simply what? 1 divided by s minus the number attached to the exponential function. So this is the second table of standard value you need to know. Okay, you just have to know it without solving. When we go down into differential equations or partial fractions using Laplace transformation, you don't need to be resolving all of this. You just have to know that Laplace of exponential 2 is simply 1 all over s minus 2. And in the case of a constant value, Laplace of 1 is simply 1 all over s. Laplace of 10 is simply 10 all over s, and so on. So the final table of standard value we are going to be doing is, alright, so the final table of Laplace transformation values which we are going to be doing for this video is the Laplace of a function raised to a constant. So if we have a function raised to a constant, then how do we find a Laplace transformation? For instance, let's say we're given the function f of t to be equal to t to the power of n, where n is an integer, okay, where n is an integer, simply a number, where n is an integer. So you have a function t raised to what? A number n. How do we carry out this Laplace transformation? It's very simple. Same idea. Laplace of t to the power of n is now equal to, remember, integral from 0 to infinity. We append in place of f of t now becomes t to the power of n times exponential minus st multiplied by dt. In this case now, we simply employ our what? Product rule, because you have two functions multiplying one another. Remember, I always say, let u be the given function, and the given function now is t to the power of n, and therefore dv is simply what? Exponential minus st dt. Alright, so this is dv, the whole of this exponential minus st dt, that gives you dv, and of course u is equal to t to the power of n. The given function becomes what? U. Now from the formula, we need to find what? V, and we need to find the u. How do you find the u? Simply by differentiating u. So if I differentiate u, I'm going to have, remember, the rule of differentiation, use the power n to multiply the variable t to the power of n, then subtract 1 from the power minus 1. I have this. So du is simply nt to the power of minus 1 times dt. I have this, okay? Now to obtain the v, because we need to find v. To obtain v, we have to what? Integrate dv. If you integrate dv, you get v. So simply you're integrating what? You're simply integrating exponential minus st dt. So if you integrate dv, you simply have v, and dv is equal to this. So you're actually integrating what? Exponential minus st dt. And if you do that, you're going to have that v is equal to integrate an exponential function once more, differentiate the power, use that derivative to divide the exponential function itself. So if I differentiate minus st, I'm simply going to have what? Minus s. Then use that value to what? Divide the exponential function. So this simply gives us exponential minus st all over minus s. So this becomes our v. All right. So if this is v, you can now plug into what? The integration by parts formula, which is simply this. Let's do it over here and see. All right, so this means integral of u dv is now equal to, so we simply say from the formula uv, what is u? U remains t to the power of n. What is v? This is what we obtain as v. So we have t to the power of n multiplied by v's exponential minus st all over minus s, okay? Minus integral of v du. What is v now? V is equal to this, remember, minus integral of v du, and v is equal to this. Du is simply nt to the power of n minus 1 times dt. So let's put down the equations. Now we have, in place of v, exponential minus st all over minus s times du. Du simply gave us this, n t n minus 1 times dt. I have this. Now, n is a constant, minus s is also a constant. Let's pull them out. That means integral of u dv is equal to, this is minus t to the power of n exponential minus st all over s. Mind you, I'm taking this negative sign up. Okay. Again, this negative times this negative here becomes plus. This is now plus. N comes out, it becomes n all over s integral. Let's rearrange the equation a bit. This becomes integral of t n minus 1 exponential minus st dt. All right. Now, at this juncture, this is integral. This is integral. What is u? We said u is equal to t to the power of n. Let's represent everything we have. integral t to the power of n multiplied by dv, and dv is simply what? Exponential minus st dt. So in place of dv here, we have exponential minus st dt, and this actually gave us minus t to the power of n exponential minus st all over s plus n all over s integral t to the power of n minus 1 exponential minus st dt. We have this now, but the integral we're evaluating is supposed to be from 0 to what? Infinity. So let's put in the limit from 0 to infinity. We simply put in the limits now. Remember, this integral also contains from 0 to infinity. Hence, for this other part we've solved, let's effect the limit. Integral from 0 to infinity of t to the power of n exponential minus st dt is now equal to, so we'll put in the limit now. Okay, we'll put in the limit, minus t to the power of n exponential minus st all over s plus n all over s integral from 0 to infinity t to the power of n minus 1 exponential minus st dt. Limit is from 0 to infinity. Now, integral from 0 to infinity t to the power of n exponential minus st dt is now equal to, since we've already evaluated this part, let's effect the limits on this other part. Here we still need to carry out our integration. So let's work on this part that we've already integrated. We have now, wherever you see t, put in upper limit. I'm going to do all of them together at once to save time. So you put in upper limit minus lower limit. This is minus t to the power of n. In place of t, upper limit is what? Infinity, minus lower limit is 0, all to the power of n, times exponential minus s, okay, t. In place of t there is upper limit minus lower limit. So you have minus upper limit is infinity, minus lower limit is 0, multiplied by t. Multiply by s. All right, all over s plus n all over s integral from 0 to infinity t to the power of n minus 1 exponential minus st times dt. So we are still to integrate this. That's why we're not effecting the limits here yet. We're just working on the ones we've already integrated. So notice that integral from 0 to infinity t to the power of n exponential minus st dt is equal to infinity minus 0, of course, is 0. 0 to the power of n also is 0. 0 times everything here becomes 0. Divide by 0 is 0. So we simply have what? 0 plus n all over s integral from 0 to infinity t to the power of n minus 1 exponential minus st times dt. And of course, we can rearrange that. If we effect 0, we can now have that. Okay, so if we add that with 0, we are going to obtain that integral from 0 to infinity of t to the power of n exponential minus st dt is now equal to n all over s integral from 0 to infinity exponential, t to the power of n minus 1 exponential minus st dt. Now, comparing these two equations, they look quite alike. The only difference is that n has now been replaced by what? N minus 1. Because if you look on the left side, you're seeing t to the power of n, whereas on the right side, you're seeing t to the power of n minus 1. So both of them quite look alike. So this means that let's call this equation 1. Let's simply call this one equation 1. And then we simply say, let I to base n be equal to what? Integral from 0 to infinity t to the power of n exponential minus st dt. If we call this I, then this simply means, like I said, this simply means that I to base n minus 1, when n has been replaced by minus 1, this actually gave us what? Integral from 0 to infinity t to the power of n minus 1. We are now replacing n there by what? N minus 1. And that is what gives us this integral, t n minus 1. So wherever t appears now, it becomes what? N minus 1. Exponential functions remains the same, exponential minus st what? dt. Now, if you have this now means that equation 1, therefore, equation 1 becomes now, equation 1 becomes, that's the very first equation now becomes what? In place of this equation, remember the whole of this is in. So you simply have in to be equal to what? N all over s times the whole of this. And the whole of this, we called it was in minus 1. So you have n all over s times in minus 1. Call this equation 2. Okay. Now, notice again that if I replace n by n minus 1, let n be equal to n minus 1 once again into equation 2. Now into equation 2. Now if we say let n be also equal to n minus 1, that means wherever you see n, put in the value as n minus 1. That means in place of in, it becomes n minus 1 in place of this n, and this is equal to, I have an n here, this becomes n minus 1 all over s times I. In place of this n, this is n minus 1, not forgetting there is minus 1 here, minus 1. So this simply implies that n minus 1 itself is now what? N minus 1 all over s times n minus 1 becomes n minus 2. Call this equation 3. Let's also continue like that. Let's say let n be also equal to what? N minus 1. So wherever you see n, put in the value as n minus 1. Now I have here n minus 1. This becomes n minus 1. We said let n be n minus 1, but not forgetting there's minus 1 here, so it becomes minus 1. And this is equal to same thing here. This is n now. This n can now be called n minus 1. Remember there's minus 1 there, so minus 1 all over s times I have here n, and n should be called minus 1, and n should be called n minus 1. So I have n minus 1, not forgetting there's minus 2 here, minus 2. All right, let's proceed over here. All right, so we are simply going to have so from here this becomes what? N minus 1 becomes n minus 2. So this is n minus 2, which is equal to, here I have n minus 1 becomes n minus 2 all over x. So this is n minus 2 all over s times I. Here I have n minus 1 minus 2, n minus 1 minus 2, that gives us n minus 3. So times I n minus 3. Call this equation 4. Okay, so we can go on considering when n is taken as n minus 1 as much as you want. But let's start from beginning. Recall we said we are looking for Laplace transformation of t to the power of n. Okay, and Laplace transformation of t to the power of n, that's what we're looking for. And we said this is equal to integral from 0 to infinity of t to the power of n times exponential minus st dt. And we now said let in be equal to integral from 0 to infinity t to the power of n exponential minus st dt. We call the whole of this in. So this simply implies that Laplace transformation of t to the power of n is equal to what? In. We call this in, okay? Is equal to in. But not forgetting, we obtained, after carrying out that integral, we obtain in to be equal to what? N over s times n over s times in minus 1. We obtain in to be this. So this simply means in is equal to n all over s times in minus 1. But also not forgetting, we obtain the value for in minus 1. What is the value now? We said in minus 1 should be equal to, after solving, when we consider n to be equal to n minus 1, we obtain in minus 1 to be equal to n minus 1 over s times in minus 2. So in place of in minus 1, this is now equal to, not forgetting there is n over s, put it down, n all over s multiplied by in minus 1. But in minus 1 will give us n minus 1 all over s multiplied by in minus 2. Okay, we obtain that over here. So this gave us in minus 2 in place of in minus 1. But then we also have a value for in minus 2, as can be seen here. In minus 2 has a value which is this. So this means Laplace transformation of t to the power of n is equal to, we are continuing now from here. This is n all over s multiply here, I have n minus 1 over s, multiply. Now, in place of in minus 2, this is the value for in minus 2. So we simply have n minus 2 all over s, multiply by in minus 3. So which means we can continue going. Of course, we can find the value for in minus 3. Now, notice that the integer or the number, remember we said let n be an integer, or which is simply a number. It's actually a number, but this number is reducing by 1 as they multiply themselves. From that number, n, it reduces by what? 1. This reduced by another 1. That means the next number will also reduce by what? 1. And it continues reducing like that by 1. So, if you remember what the idea of factorial is, factorial is simply a number multiplying itself and reducing by 1 when multiplying. For instance, if I have 4 factorial, this is actually what? 4 times, then this 4 reduces itself. I have 4 minus 1 times, this reduces itself again. I have 4 minus 1 minus 1. It continues like that till we have it up to 1. Okay? Or let's simply use, for instance, let's consider 3 factorial, and 3 factorial simply means 3 multiplied by 3 reducing again by 1. So this becomes 3 minus 1 multiplying by 3 again reduces by 1. 3 minus 1 reduces by 1. So this becomes 3 minus 1 reduces again by 1 minus 1. Okay, so you have this. So 3 factorial is actually what? 3 multiply 3 minus 1 is 2. Multiply 3 minus 1 minus 1 is simply what? 1. You have this to be your 3 factorial. The same thing happens here. I have n multiplying itself but then reducing by 1 as it multiplies. So that means in general, I can simply say that the Laplace transformation of t to the power of n is equal to what? Since n is multiplying by a reduction of itself by 1, that means it becomes what? N factorial, which means n is multiplying itself but then reducing by 1. So this becomes n factorial all over, again, for s you have s to the power of n minus 1. So it actually depends on what? How many times n is multiplying itself plus 1. How many times n is multiplying itself plus 1. So we have n factorial all over s n plus 1. So when you're asked to find a Laplace transformation of a function raised to a constant, it is simply what? The factorial of that constant divided by s to the power of n, that constant plus 1. Now let's pick up an example and see. So let's say we are asked to find the Laplace of t to the power of 5. This is actually what? It becomes 5 factorial all over s to the power of 5 plus 1. It's as simple as this. And what is 5 factorial? 5 times 5 minus 1 is 4, times 4 minus 1 is 3, times 3 minus 1 is 2, times 2 minus 1 is 1, all over s. 5 plus 1 is 6. Hence, the Laplace of t to the power of 5, remember, is going to be 5 times 4 times 2, 60 times 2, 120 times 1, 120 all over s to the power of 6. It's as simple as this. So, okay, let's say you're asked to find the Laplace transformation of t to the power of 3. It's still the same thing. It becomes now 3 factorial all over s to the power of 3 plus 1. We are working with what? This is the law. N factorial over xn plus 1. It's as simple as this. So the answer is simply what? 3 times 2 times 1 all over s. 3 plus 1 is 4. 3 times 2 times 1 gives us 6 all over s to the power of 4. That becomes the answer. Hence, whenever you're asked to find the Laplace transformation of a function raised to a constant, it is simply that constant factorial all over s to the power of that constant plus 1. So this video actually covers 3 tables of standard values which will be aiding us in Laplace transformation as we go deeper into it. Now, we've done 3. Let's just refresh our memory of the 3. The first is the Laplace transformation of a constant, and I said if you're asked to find the Laplace transformation of a constant, simply take that constant divided by s. So in the first case, if you're asked to find the Laplace of, let's say 2, this is actually what? 2 all over s. If you're asked to find Laplace of 5, it is actually what? 5 all over s. So in general, Laplace transformation of a constant a is actually what? A all over s. It's as simple as this. The second is the Laplace transformation of an exponential function. So I have, if you're asked to find a Laplace transformation of exponential, let's say 3t, is as simple. This is actually what? 1 all over s minus 3. Simple. 1 divided by s minus that number raised to the exponential function. So in general, the Laplace transformation of exponential at, where a is a constant or a number, is simply what? Equal to 1 all over s minus that number a. It's as simple as this. And finally, the Laplace transformation of a function raised to a constant. So we simply say if you have to find the Laplace transformation of, let's say, t to the power of 2, this is actually what? 2 factorial all over s to the power of 2 plus 1. And 2 factorial remains 2 all over s to the power of 3. I have this. So in general, the Laplace transformation of t to the power of n, we said is simply what? N factorial all over s to the power of n plus 1. So for this video, we've covered these three. Now the table of constant values covers about seven constant values used in Laplace transformation. In the next video, we'll talk about 2 or 3, and then in subsequent videos, we'll conclude that we can now start Laplace transformation of what? Differential equations and partial fractions. All right, guys, I will see you in the next video. Thanks and cheers.